Hello everyone, welcome to EN4593 Autonomous Systems module. In this lecture, we are going to look at the first part of Gaussian filters. Here is the outline. First, we will have a recap on what we studied last time. Then we will have an introduction to Gaussian filters, especially the Kalman filter. After that, we will learn the basics of linear systems, and next we will discuss some of the important statistics regarding random variables. Then we look at what happens when we apply linear transformations to random variables. After that, we will have a brief look at stochastic processes and how they are connected with state estimation. Finally, we will go through the Gaussian distribution. All the subject matter will help us understand linear Gaussian systems and thereby get to know Gaussian filters. In the previous lecture, our main topic was state. We now know what state variables are and how we can arrange states in a chain, and with certain assumptions we call it as a Markov chain, and we know what a complete state is and how we can use a complete state to do state estimation. Next, we went through some of the required probability theory and we looked at what conditional independence is. Finally, we studied the base filter and we did an example to reinforce what we learned. Alright, with that, let's have an introduction to Gaussian filters. So last time we saw that even though base filter looks good on paper, its practical usage is very limited. It was Rudolf Kalman in 1960 who managed to transform the base filter into a tractable implementation which can be used in many applications. He was a Hungarian researcher who had his education at MIT, United States, and he passed away 4 years ago. He published 2 landmark papers that are significantly related to the field of state estimation, and it was the second one that presented an optimal framework for state estimation in the presence of measurement noise. Peter Swerling and Richard Boocy also contributed to this work, and it is sometimes known as Kalman-Boocy filter. So since 1960, Kalman filter has been like the main workforce of state estimation for more than 50 years, and it is said to be used by NASA in the Apollo program in just 9 years later, that is in 1969. And Kalman filter is recognized as one of the top 10 algorithms of the 20th century. The reason why Kalman filter is so popular because it's an optimal estimator that can be easy to implement and it has a small computational cost. If I give you just few applications of Kalman filter, it is used in data smoothing, parameter estimation, and even phase-locked loops in radio equipments, and in GPS receivers, and there are many more. Now we can derive the Kalman filter mainly in 2 ways. In fact, Rudolf Kalman approached the problem from a least square perspective, whereas we can also formulate it using the Bayesian interpretation as well. Since we have an understanding of the base filter, we will look at it from the Bayesian viewpoint. Okay? Of course, we are not going to derive it in this undergraduate module, but still we will obtain very useful insights on how it works. Here we again have the base filter we studied before, and there are 2 steps if you can remember, the prediction step and the correction step. Okay. Now, if the previous belief is Gaussian, so I'm saying that if this guy is Gaussian, and if the probability density of the state transition model is also Gaussian, so this is that one, then we can show that the resulting intermediate belief, which we call as the Bell-XT bar, is going to be Gaussian as well. Okay, next, together with this intermediate belief, so this one was Gaussian from the previous step. Now if the probability density of the measurement model is also Gaussian, so here we also have another Gaussian, then we can show that the resulting belief Bell xt is going to be a Gaussian probability distribution as well. Okay. So the idea of the Kalman filter is simple as that, even though the derivation is a little bit involved. Okay. So basically, when the system dynamics is linear Gaussian, we can transform the Bayes filter to Kalman filter. So the question is, how does Bayes filter become tractable when the system dynamics is linear Gaussian? So the answer is pretty straightforward, because let's say we have a Bayes filter and we have the control input, and this is governed by Gaussian distribution with the parameters mu and sigma. Then we have measurement, it is also governed by the Gaussian distribution, so it also has a different mu and a sigma. And finally we have our previous state xt minus 1, and that is also according to Gaussian distribution, which has the parameters mu and sigma. Okay, and we just said that our output is going to be distributed according to a Gaussian distribution which has the parameters mu and sigma. Okay, of course we are talking about different mu's and sigmas. So when the output is Gaussian, that means we are going to get a closed form solution at each iteration. Okay, so if I take the one-dimensional case, I will have a Gaussian distribution. So this is 1D, and I will have mu and a sigma, which are my two parameters. Okay, and because of this, we say that Kalman filter is a parametric filter. Okay, so the Kalman filter requires the system to be linear. Let's have a brief overview of linear systems. It has been more than 2 centuries man has been studying linear systems and linear algebra, and we have a wealth of knowledge and mathematical tools about it. That is, linear system theory is well understood for estimation and control problems by now. Having said that, many processes we encounter in real life have some kind of non-linearity associated with them. To make use of all the linear system knowledge we have, that's why we still try to linearize those systems. We can represent a continuous time deterministic linear system by the following equations. So first we have x dot equals ax plus bu, and next we have z equals cx. So here x is the state vector, u is the control vector, and z is the output or the measurement vector. Now if we consider the matrices, A matrix is known as system or state transition matrix, B matrix is the input or the control input matrix, C matrix is the output or observation matrix. So these three matrices can be time varying as well, and still the system will be linear. Okay. If A, B, and C matrices are constant, then we can have a solution to the above equation given as xt equals e to the power a t minus t naught times x t naught plus integral t naught to t e a t minus tau b u tau d tau. and zt would be as it is. Okay, and here t naught is the initial time of the system, usually taken as 0. Okay, now you can prove this as an exercise, and I can give you a hint. So when you learn first order differential equations, I think you have come across something called first order linear equation, and it is solved using integration factor. Okay, so first order linear equation using integration factor. Now here another thing to note is that what is present in this term as well as in this term is a matrix, right? So we call this as a matrix exponential. If you haven't come across that in your linear algebra lessons, EA is pretty much having the same structure as the default exponential function, but instead what we have here is I plus A over factorial 1 and A squared over factorial 2 and so on. Okay, so this is going to be a matrix at the end. Okay, even though the real world systems are continuous time processors, state estimation and control algorithms that we implement always use digital electronics. Therefore, we need to transform continuous time dynamics that can be seen in these equations into discrete time, which is known as discretization. Now we are going to perform discretization. So I will take t equals tk, which is some discrete point in time, and also I will take t naught to be tk minus 1, which is the previous discrete point of time. Okay, then I will also assume that we have a constant control input throughout that particular interval, and with those two we can obtain this equation. Okay, here you can see that t becomes tk and t is tk, t naught is tk minus 1, and this is tk minus 1. Okay, and the limits will change from tk minus 1 to tk, and here I have again tk, and that constant control input, this one, I have taken it as u tk here. Okay, now if we define delta t equals tk minus 1, and I will introduce a variable alpha which is equal to tau minus tk minus 1, and if we do the substitution for this equation, we get x tk on the left hand side is equal to EA, and there I have delta t. Okay, and next I have x tk minus 1. So I'm actually writing this equation over here. Okay, so next we have plus, so the integration limits will change from 0 to delta t, and we have EA, and we get here delta t minus alpha. You can check that. and I'm going to write the remaining terms b, and the constant control input was utk, and for d tau we get d alpha. Okay, so this is equal to e a delta t x tk minus 1, that's the same first term, and I can take out e a delta t, and the integration here we have e to the power minus a alpha, and I can write this d alpha term here, and finally I have b and utk. Alright, now I'm going to rename certain terms. So the first one I can take as xk, that is basically xtk. Alright, and then this term I'm going to rename as f, and next we have xk minus 1, which is basically xtk minus 1. Okay, and next I take this whole thing here and I will call it as g, and finally we have uk. Understood? So here we have the discretized linear system. Okay, so you can see this is our previous state and this is our current state, and this is the control input, and here we have the measurement based on the state. Okay, so we already introduced f and g here, this one and that one, and actually we can further simplify this term to this one if a is invertible. Okay, so delta t is actually the discretization step size, and in the second equation actually we did nothing for the second equation, so basically this h is same as c. Okay, I think I should show how we can obtain this guy here from this one, so let me quickly show that. So if I take this integration part, I have 0 delta t e minus a tau d tau. Okay, so in the integration we have the exponential, matrix exponential, so that is I, and since we have minus a tau, the next term is going to be minus a tau plus a tau squared over 2 factorial minus and so on. Okay, d tau. So this one is actually, so if we perform the integration, this will become I tau minus a tau squared 2. I wrote it as factorial anyway, and in the next term we have a squared, and this will become tau cube over 3, and with the remaining 2 factorial this will become 3 factorial minus and so on. So this gets the limits delta t and 0. So with 0 all the terms would vanish, therefore with delta t I get I delta t minus a delta t squared over 2 factorial plus a squared delta t cube over factorial minus and so on. Okay, so I'm going to introduce an a, so this has a delta t, and you will see why I am doing that. Then I can actually include this a into this guy. Here again I have a delta t cube. Alright, so these are the terms. Since I introduced an A matrix from the front, I should have A inverse here. Okay, so we finally get, so in the brackets what we have is I minus e to the power minus a delta t. Okay, you can check that, times A inverse. So A inverse should exist to get this answer, but if A inverse does not exist, it can also happen, so then we have to stop at this step. Okay, and you will see there are special cases of A, and now this is like an infinite sum, so you might be wondering how we actually find this. Okay, so in special cases we will have, after a certain point, all these terms will become 0. So that will actually happen, for example, when a squared is 0, and thereafter a cube, a to the power 4, everything would become 0. And actually there's a special name for such matrices called nilpotent matrices, but don't worry about it. So if A inverse exists, we have this for this integration. Okay, so that is this term here. Okay, so the remaining f and b would be there. And if A inverse does not exist, we take up to this and we will collect enough terms to create this particular matrix. Okay, before we move on to the next section, I think it's a good idea to do an example to reinforce what we learned. So here we have a vehicle, and I have taken its state as x and x dot, so the position and velocity in a single dimension. Also I have a force applied to this vehicle, and we have Newton's second law coming in to describe the dynamics. Now let's represent this system first using a continuous time deterministic linear system. That is, we have x dot, so this is a vector, equals ax plus bu. Okay, this x is equal to simple x and x dot, and the control input I told you is equal to f, and the equation I have is f equals mx double dot. Alright, so I can use this state vector in the linear system. So in the left hand side what I have is capital X dot, so I will get x dot and x dot double dot here equals to some A matrix times x dot plus some B vector actually, and u is, let's take it as u. Okay, so we have to figure out what A and B are. So this is A and this is B. Now if we take the first row, I have x dot, right? And here what should we have? So I can write that as 0 and 1. Okay, and I don't need anything from the control input here. And if I take the second row, I have x double dot, right? So what should we have here? Now in the state vector, what we have is x and x dot, right? Therefore those can't contribute to x double dot, but that x double dot part will be coming from the control input. Since we have f equals m x double dot, we can write that as u divided by m. Therefore I can write 1 over m. Agree? Because my u is the force, so force divided by m, I get the acceleration. Okay, so that contributes here. So here we have the equation for the continuous time deterministic linear system. All right, so my next step would be the discretization. Okay, I need to discretize this to further analyze or implement estimation or control algorithm. So if you remember what we did, so for A I have 0, 1, 0, 0. Okay, and by the way, let's check what is A square. So I have 0, 1, 0, 0 times 0, 1, 0, 0. Now if we multiply these two, you will realize we will get 0, 0. Okay, now this is actually called a nilpotent matrix. Okay, and the good thing is after that A3, A4, everything will become 0. Okay, so we can find f. So f is equal to e to the power a delta t. Delta t is the step size or discretization time step. So we can simply write this matrix exponential as I plus a delta t plus a delta t square over 2 factorial and so on. But we saw that all this is going to be 0 because a squared is 0, right? Therefore we get 1, 0, 0, 1 plus a times delta t. So that would give us 0 delta t 0, 0, and finally we get 1 delta t 0 and 1. Okay, so pretty straightforward, right? So we have found F matrix. Next we are going to find the matrix G, but before that let's find out whether A is singular or not. So A was equal to 0, 1, 0, 0, and if we find the determinant of A, you can see that the determinant is equal to 0. So that means A inverse does not exist. Okay, so in order to find G, we will stick to this equation where we have already found F, and that was equal to 1 delta t 0, 1 times. Now we saw that these latter terms goes to 0, and as a result we can write this remaining terms as delta t 0, 0 delta t. So that matrix minus, here we have 0 delta t squared and we have the minus sign and also the 2 factorial, and then 0 and 0 here. Okay, and the B matrix was 0 and 1 over m. Now when we multiply these three matrices, we will finally get 1 over 2m delta t squared and delta t over m. Okay, so you can verify that. So the discretized model would be xk equals F matrix is 1 delta t 0 1 times xk minus 1 plus G matrix is 1 over 2m delta t squared delta t over m times uk. This is the discretized model. Okay, now if we expand this, we get xk and xk dot right, and on the right hand side we are going to get xk minus 1 plus delta t times xk minus 1 dot, and then we have half delta t squared. Let's take fk for the time being, fk over m. So this is like the acceleration term, and on the second row we have xk minus 1 dot plus delta t times fk over m. Right. Now if we look carefully, we see that the next position is equal to current position plus current velocity times delta t plus, so this is acceleration, right? So half acceleration times delta t square. So this is a pretty much known equation with constant acceleration, right? And if we consider the second row, we have next velocity is equal to current velocity plus the current acceleration times delta t, right? So that also agrees. So we discretize the given continuous model to obtain this equation, but with intuition we could have actually obtained these equations, right? And that's what we are actually going to do in our upcoming examples. For the sake of completeness, we have gone through the discretization process, but if these discretized equation can be obtained by intuition, then there's no need to actually go through all these steps. Understood? The next pillar we need to understand the Kalman filter is the probabilistic aspect. So let's have a brief overview on the important statistics of random variables. The expectation, mean or average of a random variable can be given by these equations for discrete and continuous case. If we take a very simple example of a discrete random variable, let's say x can take values 1, 2, 3, 4 and 5. Let's also assume that all these are equally probable Okay, then the expectation is going to be 1 times 1 over 5 plus 2 times 1 over 5, 3 times 1 over 5, 4 times 1 over 5, and 5 times 1 over 5, which would give us 3. Okay, so this is pretty much same as adding these together and dividing by 5. This is because they are all equally probable, right? Expectation is a linear function, and that means we have the expectation of ax plus y being equal to a times ex plus ey. Okay. The expected value of any function g of random variable x is given by e gx equals to minus infinity to plus infinity, particular function times the probability density function dx. Okay, so the px is the PDF of x. And if we want to compute the expected value of a function of multiple random variables, then what we have is, let's say the function is gxy, then we'll be using the joint probability density function, which is pxy dx and dy, right? Pxy is the joint probability density function of x and y. Okay. Variance is the expected deviation of the random variable about its mean value, and the equations are given as follows. Since the deviation can either be positive or negative, we take the squared value. Okay, and we can also show that this expression is equal to the expectation of x squared minus the squared value of the expectation of x. So if we take a simple example, let's say we have a discrete random variable taking the values 1, 2, 3, 4, and 5, and earlier we had x bar equals 3 for this one, and the variance is going to be the expectation of 1 minus the mean squared, 2 minus mean squared, and finally we have 5 minus mean squared. Okay, and this will give us the answer 2. So we have the random variable x, and there is a certain mean, and the values are deviating about this mean with a variance of 2. So this is the deviation about mean. Okay, the standard deviation is the square root of the variance, and we use the notation x bar and sigma squared, this notation, to represent a random variable x with mean x bar and variance sigma squared. Okay, when we talk about multiple random variables, the measure of joint variability is given by covariance, and the equation is pretty similar to variance, but here we are talking about two random variables, and that's why here we have x minus ex and y minus ey. Again, you can show that this is equal to exy minus ex times ey. Okay, if we do a simple example, let's say we have two random variables x and y holding these values, and we can find its mean as well. Now I can calculate the covariance. covariance x, y would be equal to the expectation of, so the first value of x is 1 minus its mean times first value of y minus its mean. So this is our first entry. Then we have 2 minus 3 and 4 minus 6. And our final term would be 5 minus 3 times 10 minus 6. Okay, and this would give us plus 4. And the reason why I have also considered the sign is that actually covariance is giving us an indication of how x and y are correlated with each other. Therefore, we define something called correlation coefficient, which is equal to covariance over variance of x and variance of y. That is like we are normalizing the covariance, and the result would be between -1 and +1. Okay, so graphically what this means is, let's say we have two variables like this, and if we take the points, when one random variable increases, the other one also increases. Similar in this case, right? So here we have a positive correlation. Okay, so we can actually find the correlation coefficient between x and y, and that would be +4 divided by square root of 2 and square root of 8, which is 2 square root of 2, and this would be equal to +1. In fact, they are perfectly correlated, and it's not surprise because y is actually equal to 2x in this case, right? If we take another random variable z, and here you can see the values are decreasing when x is increasing, and when we find covariance between x and z, it turns out to be -4. Okay, so graphically we will be having points like this for negative correlation. We can find the correlation coefficient, and it will turn out to be -1. Okay, now we can have rho equals 0, which means no correlation. For example, if we have two independent random variables, then the correlation coefficient between these two independent random variables will be 0. However, please note that the converse is not necessarily true. That means when rho is equal to 0, that does not mean the two random variables are independent. Understood? To understand Kalman filters, we should know multivariate Gaussians, and for multivariate Gaussians, we should know what a covariance matrix is. So if we take random vectors, now remember previously we were talking about random variables. So in a random vector, for each entry now we have a random variable. Okay, so this one here is a random variable, and a random variable. Okay, for example, let's say we want to find the localization of a mobile robot. So for the state vector, I may have something like x, y, and theta, where these entries x, y, and theta are random variables, and all together we have a random vector. Okay, now the covariance between such two random vectors will become a matrix, which we call as the covariance matrix. The expression for covariance is again similar to previous one, but here we are dealing with random vectors, and that is why we have a transpose here. Okay. Now when the second random variable, so it is y in this case, is equal to the first one, then we call this as the autocovariance. So when y is replaced by x, we call this as the autocovariance. But nowadays we don't really use that term often. Okay, so we basically call it as a covariance matrix as well. So here we have an example covariance or autocovariance matrix. Okay. So one thing we immediately notice is that the covariance or the autocovariance matrix is symmetric. So let me write symmetric. That is, here you can see this term is same as this one. Of course, the order of the multiplication has changed, and if you take this term, it's same as this one, and so on. Okay. Now, if you are seeing this matrix for the very first time, it looks pretty intimidating, but let's try to clearly understand what it really is by going through the entries. Okay. So in this covariance matrix generated for a state random vector x, first let's look at the diagonal. Okay, so I'm considering the diagonal terms. So what do we have in the diagonal? If we carefully look at the diagonal terms in this matrix, you will realize those are the variance terms. So in fact, if you take the first element here, it's the variance of the random variable x1, right? That is how random variable x1 is spread about its mean. So we are talking about this guy. Okay. Next we have the variance of x2. Okay. And finally we have the variance of xn. So how it is deviating about its mean. All right. Next we'll move on to the off-diagonal terms. So what can you say about these off-diagonal terms? So if you carefully look at it, you will realize those are the covariance terms, right? Now in particular, if you take this guy, it's the covariance between x1 and x2. So that tells the relationship or the correlation between these two random variables. And similarly, if you take, let's say this one, it says the correlation between x2 random variable and xn random variable. Simple as that. Okay. So I guess now you understand each and every entry in this matrix, and you won't be intimidated no matter how big the matrix is, right? And in fact, you will realize later that this matrix can even be 1000 by 1000 when we deal with applications such as SLAM. Okay. Another important fact about the covariance matrix is if we take any n element column vector Z and evaluate Z transpose covariance matrix times Z, we have Z transpose times the expectation of x minus x bar times x minus x bar transpose times Z, and we can insert Z inside this expression to obtain Z transpose x minus x bar times x minus x bar transpose Z. Okay, and this is equal to the expectation of Z transpose x minus x bar, and the next term is actually the transpose. So we can write this as Z transpose times x minus x bar whole thing transpose. Okay, so it's the same term that we have here, transpose. All right. Now you will see that this is actually a scalar, because what we have here is a row vector times a column vector. So this is going to be a scalar, and therefore this is a scalar as well. So that would give us the expectation of Z transpose times x minus x bar, this whole thing squared. All right. And since it's a square of a scalar, this would be greater than or equal to 0. When the covariance matrix has this property for any vector z, we say that it is always positive semi-definite. Okay, and later this will become useful when we deal with multivariate Gaussian distributions. All right. Next, we will have a quick look at how probability density functions get transformed under a given function. Let's say we have two random variables x and y, and they are related with each other by monotonic functions g and h. By the way, do you know what a monotonic function is? So we say that if the slope of function is always positive, then the function is monotonically increasing. And on the other hand, if the slope is always negative, the function is monotonically decreasing. Okay, so here we have y equals gx, and x would be equal to g inverse y, and we can call that as hy. All right. Now, if we know the probability density function of random variable x, then we can compute the probability density function of y as follows. So the argument is, let's say the probability of x for a very small range dx would be px dx, safely ignoring the integration as dx is very small. Okay, now x and y are connected, therefore for the dx there will be a corresponding range dy related by the given function, and as a result the probability of y in that range should also be the same. So this would be equal to py dy. Okay, so from this we can write the probability density function of y, py, is equal to dx over dy times px. Now one thing to note is that y can either increase or decrease when x is changing. All right, therefore we'll be actually considering the absolute value of this one, and we can further write this as, so from the above function we have x equals hy, therefore we can write dx over dy as h dash y. Okay, and because we want to get rid of all the x's here, and x is going to be hy. Okay, so we get this equation and we'll be using it later. Okay, next we will quickly go through stochastic processes, as we are actually dealing with such processes in probabilistic state estimation after all. So the word stochastic simply means the random nature of the process. So what is a stochastic process? It is nothing but a random variable that changes with time. So if we have the time axis t, and at t equals t1, we may have a PDF for x. So this is x t1, and let's take the PDF to be something like this. Okay, and similarly at t equals t2, x T2. Our PDF may slightly change, and let's say it's something like this. All right, and ultimately if we take xtn, again we'll have something like this. All right, now we treat xt1 and xt2 as two different random variables because each one has its own PDF, right? Now if we consider the mobile robot localization example once again, it's actually a random or stochastic process, right? So with time, the PDF of X is changing as given in this figure. Understood? So there are four types of stochastic processors. First, we have continuous random processors. So in that, the random variable is continuous as well as the time is continuous. For example, if we consider the temperature at each moment of the day, we see that the temperature is continuous and the time is continuous. Next, we have discrete random processors. So the random variable has discrete values while the time is continuous. For example, if we count the number of people in a given building at each moment of the day, then that is going to be discrete while time is continuous. We also have continuous random sequences. So in that, the random variable is continuous, but we are taking time in a discrete manner. For example, the highest temperature at each day is continuous, but since we are counting each day, it's going to be discrete in time sense. Okay. The final type is the discrete random sequences. So in that, the random variable is discrete as well as the time is discrete. For example, the highest number of people in the building each day is going to be discrete, and we are counting day by day, so that's also discrete. Now in this module, we will be mainly looking at continuous random sequences and discrete random sequences. For example, the localization problem we have been discussing so far is a continuous random sequence. So in that, we have the state comprising continuous random variables, but we are considering time in discrete manner. And for the discrete random sequences, we can consider something like sensor status, and that can have random variables, let's say AT, BT, so on. So those will have discrete values, and we are considering time in discrete manner as well. The final topic we will look at is the Gaussian distribution. In probability theory, a normal or Gaussian distribution is a type of continuous probability distribution for a real valued random variable, and it is given by this equation. Here x is actually a scalar. The parameter mu is the mean or the expectation of the distribution, while sigma squared is the variance of the distribution. Now Gaussian distribution is important because according to central limit theorem, the average of many samples or observations of a random variable with finite mean and variance will have a distribution that converges to a normal distribution as the number of samples increases. And due to this reason, we actually model many natural phenomena using Gaussian distributions. So graphically, it has this nice symmetric shape around its mean, and you can see about 68.3% of the values fit inside 1 sigma range, and if we consider 3 sigma, then almost all the values, that is 99.7% of the values, fit in that range. Let's say we generate random variable y using a linear transformation applied to random variable x. So we have y equals gx equals ax plus b. Then we have x equals hy, where hy is going to be y minus b over a. That's pretty straightforward from this part. And if we consider the derivative of hy, we get 1 over y, right? And from what we learned previously, we can find the probability density function of y using this equation. So this one is 1 over a, and here we have the Gaussian distribution for x, where we replace x by this guy. Okay, and as a result we obtain this equation, which is a Gaussian as well. So we can say that the random variable y is going to be a Gaussian distribution with the mean of ax bar plus b, which comes from this linear function, and the variance is going to be a squared sigma x squared. Okay, so a linear transformation of a Gaussian random variable results in a new Gaussian random variable. So this is very important when we formulate the Kalman filter. When it comes to random vectors, we will be dealing with multivariate Gaussian distributions. For example, if I take a certain state x, which has x and y as the two random variables, so this is a random variable and this is a random variable as well. So the Gaussian distribution over such a state would have the following structure. So it pretty much resembles the Gaussian function we had for the scalar, but you can observe here x is a vector and mu is also a vector, and here comes the covariance matrix, actually the inverse of that, right? And here we have the determinant of the covariance matrix. So I will write this as the covariance, and n is the dimension of vector, and here we have the determinant. Now you may recall that if we consider this guy here, what can we say about it? Now the covariance matrix, and in fact its inverse, is a positive semi-definite matrix, and therefore this is going to be greater than or equal to 0, which is needed for the Gaussian distribution, and the covariance matrix actually ensures that, right? So here covariance matrix and also its inverse are positive semi-definite. Okay, now we can actually graphically visualize only up to n equals 2. So if I consider that example, here on the left hand side we have the 3D view of the multivariate Gaussian distribution when n equals 2. Let me write n equals 2, and here we have a top-down view of the same distribution, and for the axes I have x and y, and this is going to be x bar and this is y bar, the mean. Okay, so mu vector is actually x bar and y bar. Okay, similar to what we had before, when we input a multivariate Gaussian random variable into a linear transformation, hopefully we should get a multivariate Gaussian random variable, right? So we can start off with x equals to hy. Now something to note is that here we are dealing with matrices, therefore x would be equal to a inverse y minus a inverse b. Let me quickly go through the derivation. So we start off with this equation, but here we have some changes. Now for the derivative, of hy. Previously we had the absolute value, but here the determinant is coming in. Okay, and this part here is x. Okay. Okay, the next step is we have introduced an identity matrix that will change nothing. Okay, and meanwhile, I hope you know that the determinant of A times the determinant of A inverse is equal to 1. Therefore, this A inverse determinant goes here as A determinant. Okay, and meanwhile, you can see that we have taken this part to be A inverse expected value of y. Okay, so those are coming from the properties of linear systems. Next, what we do is we also know that the determinant of A is equal to the determinant of A transpose, and we have divided this A determinant into this guy and that guy. Okay, and meanwhile we have taken the transpose here and we have taken out A inverse with the transpose, which becomes this. Okay, so with those we finally get this multivariate Gaussian distribution for y, where the mean is equal to ax bar plus b, and see how the covariance matrix has changed using the A matrix. Okay, if we go back to the multivariate Gaussian distribution with n equals to 2, we can get some more insights from its graphical representation. For reference, let's take the covariance matrix having variances equal to 1 for both dimensions. Okay, and we have a top-down view here and we see a nice circular cross-section. Now what will happen if individual variances increase, like in this case? Of course, you know that the spread will be large and therefore we will see a larger circle. And what about when variance decrease? Obviously it will get shrunk and we will have a smaller circle from top. Now one thing to note here is in all three cases the correlation or covariance between the two random variables are 0. So here and here you can see no correlation. This is high variance and this is low variance. Okay. What will happen when one random variable has high variance than the other one? In that case, we will lose the circular shape towards that dimension, right? And on the other hand, if we swap the dimensions, the shape will be the opposite. So here we have high variance in second dimension, and here we have high variance in first dimension. Still, you can notice there's no correlation between the two random variables, right? Finally, if I introduce some covariance, or in simple words, if the two random variables have some connection between each other, what will happen to the shape? So what I'm saying is, in my covariance matrix, now there is some correlation. Okay, so this is positive correlation. So what would be the shape be like? Now since there is positive correlation, the shape would get skewed in this direction. That is, when x increases, y would also increase. Okay, and what if I have more correlation, what would be the shape? So here I have high positive correlation. So the shape I would obtain would be sharper than this one, right? Now another interesting observation would be to notice that the vertical spread as well as the horizontal spread remains same for all these three figures because we are having equal variances for both random variables. What I mean is, if I take this and that, so you can observe more or less this spread, let's call it as vertical spread. So it's same for all three, and also we have the same spread in the horizontal direction as well, right? So this and that. This is the horizontal spread. Understood? So following the same idea as before, if we have a negative correlation, then our shape would be skewed in the opposite direction, and if the correlation, the negative correlation is higher, we will have a sharper figure. Okay. With that, we have come to the end of this lecture. We introduced Kalman filter as the earliest tractable implementation of Bayes filter for continuous spaces, and it has been used as the workhorse for estimation for more than 50 years since its beginning. Now, to transform Bayes filter to Kalman filter, we need linear dynamics, and we also need Gaussian probability distributions. So we studied linear system theory necessary to formulate Kalman filter, and next we discussed some of the important statistics regarding Gaussian random variables. So with this lecture, we went through all the supporting material required to formulate the Kalman filter, and now we are ready to take the next step towards Kalman filter in the next lecture. Thank you.